Litz wire losses. Litz wire is used to reduce winding losses at high frequency. In this example, Litz wire consists of 7 insulated transposed wires. Total cross-section area of the Litz wire is 0.126 mm squared. This wire is used to wind the solenoid on the ferrite core. The solenoid is energized by the alternating current with earth mean square value of 1 ampere and the frequency of 100 kHz. Our task is to calculate losses in the winding. Okay, let's start QuickField now. In QuickField I create new problem. Litz. Next. Problem type is AC magnetics. Frequency is 100 kHz. Model class is axisymmetric. Length units are millimeters. And I will need an electric circuit to specify the conductor's connection. So type in the circuit file name here. Circuit 1. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You should draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. Here's the file, and I will import it. The geometry is imported. You can see the cross-section of the solenoid. In axisymmetric problems, the axis of the rotation is a horizontal one, and we should draw only the upper half of the cross-section. Here you can recognize conductors, insulation, and the core. In fact, the magnetic field is distributed not only in these parts, but also in the air outside. QuickField cannot simulate magnetic field distribution in the infinitely large space, so we need to restrict the simulation area. Switch to insert mode and draw the air block boundary. Horizontal line along the axis here. Change the line type to half arc and draw the half arc here. Zoom to fit. Next I'm going to assign labels. Through labels I will provide material properties. Switch to select objects mode. Click the object to select. This is the air. Let's zoom in. Switch the zooming mode off. Click here. This is the core. This is the insulation, and inside the insulation we have the conductors. I'm going to assign individual labels to each strand. Would be strand number 1, this is strand number 2, strand 3, strand 4, strand 5, strand 6, strand 7. Remember that wires are transponded, so in the next cross section the wire's position will change. Let's shift strands by 1 position. Now I have strand 2, this would be strand 3, strand 4, strand 5, strand 6, strand 7, strand 1, and so on in the next cross section. This would be strand 3, strand 4, strand 5, strand 6, strand 7, strand 1, strand 2, and so on for all other conductors. Okay, I have finished assigning labels to the strands. If you click the label in the tree, you will see where conductors are located. Note these beautiful waving patterns here and here. Okay, that is all for block labels, but we should also assign labels to the external boundary. Zoom to fit, click here, external. QuickField automatically assigns proper boundary condition on the axis of the rotation, so I do not assign label to the axis. Now I am going to provide physical properties for the labels. Double-click the label name in the tree. Relative magnetic permeability of the air is 1. Relative magnetic permeability of the insulation is 1. Core is made of ferrite with a relative magnetic permeability of 500 and 0 electrical conductivity. Conductors are made of copper with a relative magnetic permeability of 1 and electrical conductivity of 57 megasiemens per meter. As you saw, there are several conductors with this label, and I will specify that these conductors are connected in series. I should not specify any field source here, because we have a co-simulation with the electric circuit, and all conducting blocks from the model should be included in the electric circuit. Okay. I will specify the same copper properties for other strands. Permeability, conductivity, connected in series. Connected in series. Far away from the solenoid, magnetic field fades to 0, so for the external boundary I specify 0 magnetic potential. Okay. That is all for material properties. We have only to build the finite element mesh, just press this button, and the field simulation part is ready. Remember, we have a co-simulation with the electric circuit. So I will open the circuit file. Okay. Here I should place all conducting blocks. Strand 1, strand 2, strand 3, strand 4, strand 5, strand 6, strand 7. Next I will add the current source and connect the strands in parallel. Total current value in all strands is 1 ampere, which is root mean square value. In QuickField I should specify the peak value, so here I will multiply by square root of 2. Okay. Now that is all. I should save all problem files and run the analysis. The problem has been solved. Let's take a look at the results. Here you can see the magnetic field lines and the color map of the current density. Let's zoom in. You can see that the current density distribution is not uniform in the conductors. That is caused by the eddy currents in the conductors. I'm going to use the contour tool to select conductors and calculate some integrals. Follow to the integrals. Total current. This is the peak value, square root of 2, as we have specified, and I can calculate the joule heat. This is for the one turn of the Litz wire. To calculate losses in the entire winding, I should select all conductors. There is no need to click all conductors one by one. I will clear the contour and construct new contour from the straight lines. Click and drag here and here. Contour close. Remember, you can calculate volume integrals only for the counterclockwise directed contours. Contour, change direction. Now here I can calculate the joule heat. These are the joule heat losses for the entire winding. Beside the field simulation part we have an electric circuit. Here you can calculate current and the voltage for each element. And if I measure the voltage drop on the source and the current value, I can calculate the power produced by the source. I will use complex power impedance calculator that you can find on our website. So the voltage real part 0.24, imaginary part 11.3, current 1.414, 0. Calculate. Active power is 0.17 watts. And about the same value you have seen when you calculate the joule heat integral in the winding. Okay, what else you can do here? Contour, clear. Here you can adjust the field picture. For example, I will switch on the color map of the flux density. Okay. The correspondence between the colors and the numbers you will see in the legend, and the exact values you can get in any point using the local values tool. Just click any point or edit the point coordinates here, and you will get the flux density value, current density value if any, and other field parameters. You can also use the contour tool to calculate integrals and to get the field distribution along the contour on the XY plot. For example, here I will click to select this edge, click to select another edge, open the XY plot, and here I will get the flux density distribution along the solenoid axis. The exact values you can see in the table. Coordinates, flux density components, and other field parameters. If you search for the Litz wire on our website, you will find the example page. Here you can read about problem setup. In fact, two solenoids are compared here with the Litz wire and with the solid wire. You can see the resulting pictures here, and you can download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.